Welcome back, students. We are done with the lesson for the most part, except the problems. So I'm going to do the problems now. I'm not going to do the first two problems because they are theoretical and the explanations of those problems are given already in your textbook. So if you refer to the textbook, the answers for those problems, then you will be able to understand the problems. In fact, you will be able to answer those problems, most of the questions in the problem straight away. If you have any questions regarding those two, then get back to me, then I'll explain them to you. But otherwise, the answers are already given in the textbook. So if you go through the textbook, you will understand those answers. So I'll start from problem 5.3. Okay, let's do exercise problem 5.3. A short bar magnet placed with its axis at 30 degrees with a uniform external magnetic field of 0.25 Tesla experiences a torque of magnitude equal to 4.5 into 10 power minus 2 joules. It's given as joules, but the unit for torque is not joules, it's Newton meter. So there's a difference. So it's wrong in your book. So it is 4.5 into 10 power minus 2 Newton meter. What is the magnitude of magnetic moment of the magnet? Well, this is a very easy question to do. So you have a short bar magnet placed with its axis 30 degrees with a uniform external magnetic field. So I am doing 5.3 now. 5.3. So you have a short bar magnet, okay, and it is placed in an external magnetic field at an angle of 30 degrees. This B value is given, which is 0.25 Tesla. So B here is equal to 0.25 Tesla. But this is external. This is not the magnetic field of the magnet. And it is experiencing a torque of magnitude equal to 4.5 into 10 power minus 2 Newton meter. So the torque experienced by it is equal to 4.5 to 10 power minus 2 Newton meter. Okay. Now the question is, what is the magnitude of the magnetic moment of the magnet? That's very easy. So we know the torque is equal to mb sine theta. So this is 4.5 into 10 power minus 2 Tesla, which is equal to m. To B, the external magnetic field is 0.25 Tesla. So 0.25 into, and then sine theta is sine 30 degrees. So that is sine 30. This is going to be 1 by 2. So this will be 1 by 2 clearly. I can take all these quantities to the other side and find m from this, and that's very easy to do. What is m? So 2 will go there, so it will be 9 into 10 power minus 2 by 0.25. Okay, so if you do that, it would be clearly, it's like 90 by, I'll do it this way. So this would be 9 into 10 power minus 2 by, and this would be 25 into 10 power minus 2. So this will cancel. So 9 by 25, and that is going to be equal to 90 by 25 into 10 power minus 1. So I am multiplying by 10 and dividing that by 10. So if I do that, so m is going to be equal to, so 325 is 75, can reduce that. So 325 is 75. And what is left? So 15 by 25, so that is 3 by 5, so that would be 0.6 into 10 power minus 1, and that's going to be equal to 0.36 ampere meter square. So this is a very straightforward problem. There is nothing great about it. So using the formula you can do this. And let's do problem 5.4 now. A Schwarzschild magnet of magnetic moment M is equal to 0.32 joule per Tesla is placed in a magnetic field of 0.15 Tesla. If the bar is free to rotate in the plane of the field, which orientation would correspond to its stable and unstable equilibrium? What is the potential energy of the magnet in each case? Again, it's a simple problem. 5.4. So you have a bar magnet of magnetic moment and is placed in a uniform magnetic field of so much. So if the bar is free to rotate in the plane of the field, so let's say this is the external field. In this external field, this is B external, which is equal to 0.15 Tesla. So 0.15 Tesla, and you have a magnetic moment 0.32 joule per Tesla. So this is equal to 0.32 joule per Tesla or ampere meter square, both are same actually. Joule per Tesla. Anyway, so that is given. Now this is free to rotate in the plane. So the question now is, which orientation would correspond to its stable and unstable equilibrium? Clearly, if this is the north pole, north and south, then this has to align with this. If it is aligned with the external magnetic field, and that is where you will have the stable equilibrium. So if it is aligned, then even if it is stable slightly, then it will come back to the same position. So it will try to come back, but the oscillation will happen, but that is the stable equilibrium. What is unstable equilibrium? When it is on the other side. So when it is, if north is in this direction, it's pointing in that direction, then when you slightly disturb it, then it will go all the way, and then it will try to align with the field. So that is the unstable equilibrium. So 0 degree will be stable equilibrium, 180 degree would be the unstable equilibrium. And so you answered those questions A and B. So 0 degree is stable equilibrium, and 180 degree will be unstable equilibrium. Unstable equilibrium. And what is the potential energy of the magnet in each case? And that's the third part. So what is the potential energy? We have already derived the formula. So potential energy U or PE into minus mb cos theta. So you have these numbers, plug in. So in the stable equilibrium, when it is 0 degrees, stable equilibrium, so the potential energy is equal to minus m is 0.32 and b is 0.15 and cos theta, so cos 0, so that is 1. So you are going to get what I'm going to get now. So I'll get this will be, if I multiply this, then I get minus, I just do 1, 10 power minus 1 is there now. Okay, I'll just do it this way, 0.32 into say 1.5 into 10 power minus 1, keep it like that. So this will give me minus 0.48 into 10 power minus 1, or this will give me minus 4.8 into 10 power minus 2. Okay, so hopefully, so that's the potential energy joules. And unstable equilibrium, so P at 180 degrees, so unstable, equal to say minus mb cos theta, and that should give you so minus 0.32 into 0.15. Now it is cos 180. Cos 180 is going to be minus 1, it's going to be a positive number. So you get the same thing, but it is positive. It's 4.8 into 10 power minus 2 joules. So one is minus 4.8 and the other one is 4.8 into 10 power minus 2. So notice that the potential energy will be minimum, minus 4.8, when an object is in stable equilibrium, and maximum when it is in unstable equilibrium. Hope this is clear to you. Now let's do problem 5.5. A closely wound solenoid of 800 turns, an area of cross section 2.5 into 10 power minus 4 meters squared, carries a current of 3.0 amperes. Explain the sense in which the solenoid acts like a bar magnet, and what is its associated magnetic moment. Well, we have already discussed the first part of the question. It explains the sense in which a solenoid acts like a bar magnet. We have covered that already. When we did the lesson, we did that. So refer to that video to know the answer. It's a very straightforward answer too. Next one, what is its associated magnetic moment? That's easy to do. So 5.5. The number of turns in the solenoid is equal to 800, total number of turns. And then the area of cross section is 2.5 into 10 power minus 4 meters squared. So the area is 2.5 into 10 to the power minus 4 meter squared. The third part is the current is 3 amperes. So I is 3.0 amperes. Now the question is, what is its associated magnetic moment? We know it. So what is that? Magnetic moment M of a solenoid is given by NIA, in short, solenoid. So this is going to be equal to 800. I is 3.0 into A is 2.5, 10 to the power minus 4. Okay. It's going to be ampere meter square. Okay, so this is going to give you so this is 24 and that is 2.5, somewhere around 6, right? So it's going to be 2000. Let me just take it this way. 8 into 3 into 2.5 to 10 power minus 2. I'm getting rid of zeros actually. Okay. So if we do that, it's going to be 7.5 into 8. So two 7.5s, this will be 7.5, right? 7.5. Two 7.5s will be 15. So 4 would be 30 and 8 would be 60. So 60 into 10 power minus 2. Minus 2 or is equal to 0.6 ampere meter square. That's the magnetic moment. So it's very easy. Let me move on. to do 5.6 now. If the solenoid in exercise 5.5 is free to turn about the vertical direction and the uniform horizontal magnetic field of 0.25 T is applied, then what's the magnitude of torque on the solenoid when its axis makes an angle of 30 degrees with the direction of the applied field? Okay. So they are referring to the same solenoid that we have done here in 5.5. So 5.6 uses the same solenoid, which means that M of this is the same as 0.6 ampere meter squared. And the external field is 0.25 Tesla. So this is kept in an external field of 0.25 Tesla. So B external is equal to 0.25 Tesla. And it is kept at an angle of 30 degrees with the direction of the applied field. So it's like this. So the external field is like this. This is B. Then this is kept at an angle of 30 degrees. This is north south. Okay? So that's how it is. So they're asking you to find the torque. It's very easy to do. So this the torque is equal to mB sine theta, and here m is 0.6, then b is 0.25, and then sine 30, it's going to be 1 by 2. So it's very easy to do. So what do you get here now? So this is going to be equal to so 0.3 into 0.3 into 0.25. So that's going to be equal to 75 0.075 Newton meter. So this must be the answer to that question. Again, it's very easy to do. Let's move on to do 5.7. A bar magnet of magnetic moment 1.5 joules per Tesla aligns with the direction of a uniform magnetic field of 0.22 Tesla. Then what is the amount of work required by an external torque to turn the magnet so as to align its magnetic moment? It's normal to the field direction and opposite to the field direction. Okay, so that's easy to do. So 5.7. So what is given here is that a bar magnet of magnetic moment 1.5 joules per Tesla lies aligned with the direction of a uniform magnetic field of 0.22 Tesla. So there is an external magnetic field like this, and now this bar magnet lies aligned with this like that. So north of the bar magnet is like this, south is like that. So the magnetic moment is given. So M is given to be 1.5 joules per Tesla ampere meter squared, and let's say B is 0.22 Tesla. So B value is 0.22 Tesla. So now, what is the amount of work required by an external torque to turn the magnet so as to align its magnetic moment? That is the potential difference, right? Because the work you do is going to be equal to the potential difference. So what is the potential difference? What is the potential here when it is aligned? So when it is aligned at 0 degrees, is this way. Potential at 0 is equal to minus mv cos theta, and that is equal to 1 minus 1.5 into 0.22, 0.22. Then cos theta, since it is aligned now, it is theta is 0, so that's going to be 1. So this is the value you get. So what does this give you? So this will give you 0.22, 0.11, 0.33 is what you get. The minus 0.33 joules. So that is what you get when it is aligned. That is the potential energy at this position. And what is the question now? When it is normal to the field direction, so now you are going to take it from here to here. Okay? Then what is the potential energy at 90 degrees? At 90 degrees, so I'm trying to take this magnet here, the ball magnet, and then I'm going to turn it like this, 90 degrees. And what's the potential energy now? So potential energy 90 degrees is equal to minus mb, now cos 90. So cos 90 is 0, so the whole thing will become 0. So what have we done? So we've taken it from minus 0.33 joules to 0. Then what's the potential difference? The potential difference is final minus initial, and that would be equal to 0 minus, so the potential energy, okay, in case 1 is equal to, this is P90 minus P0. So it's equal to 0 minus of minus 0.33, and that should give you 0.33 joules. So this is a work we need to do to take it from here to this place. So this will try to align, so that this field will try to pull it back, so you're going to do work against that field. So this is the amount of work you need to do that. Okay, so that is it. The second part is opposite to the field direction. So what is it that you know, like what you have to do to take it further to the opposite direction? So now it is aligned like this. You are going to take it to the other side. Then what is the work you need to do? What is the potential energy at 180 degrees? Potential energy at 180 degrees would be minus mb cos 180. So cos 180 is minus, minus of minus will become plus, plus mb, that will give you 0.33 joules. This is minus, notice this is plus 0.33 joules, as you do here. So that's the potential energy here. So what have you done? You have gone from this potential to this potential. So what's the potential energy difference? That is the work you have done. So in the case of P2, that's going to be P 180 degrees minus P0. So that should give you 0.33 minus of minus 0.33. So that should be equal to 0.66 joules. So this is how you do this problem. The next problem is problem 5.8. A closely wound solenoid of 2000 turns, an area of cross section 1.6 into 10 power minus 4 meters squared, carrying a current of 4 amperes, is suspended through its center, allowing it to turn in a horizontal plane. Then what is the magnetic moment associated with the solenoid? Then what is the force and torque on the solenoid if a uniform horizontal magnetic field of 7.5 10 power minus 2 Tesla is set up at an angle of 30 degrees with the axis of the solenoid? Again, this is an easier problem to do. They've told you that the solenoid is 5.8. So the number of turns in the solenoid is 2000, and the area of cross section A is given to be 1.6 into 10 power minus 4 meters squared, and the current I is given to be 4 amperes. Then it is suspended through its center, allowing it to turn in a horizontal plane. So it is like this. You can turn in a horizontal plane. You can do that. And what is the magnetic moment associated with the solenoid? And that's easy. So your M is equal to N I A or NAI, I keep saying that. So 2000 into A is 1.6 into 10 to the power minus 4, and then I is 4. So clearly, if I adjust this, this is going to be equal to 2 into 4 into 1.6 into 10 to the, this is 3 minus 4, so 10 to the power minus 1. So that's how I take that. So that this would be 4 into 1.6 would be 6.4, and then twice that would be 12.8. So this is going to be equal to 6.4 into 2, 12.8 into 10 power minus 1. So 12.8 to 10 power minus 1, that is equal to 1.28 ampere meter square. So that's the first part of the problem. We have found the magnetic moment of this solenoid, which has 2000 closely wound turns. What's the second part? The second part is, what is the force and torque on the solenoid if a uniform horizontal magnetic field of 7.5 × 10 power minus 2 Tesla is set up at an angle of 30 degrees with the axis of the solenoid? Okay, so this part is, you have an external B, and in that you keep the solenoid at an angle 30 degrees. So this is the direction of M, and this is B, and the angle is 30 degrees. Then what's the force? That's the question. Okay. So clearly, the force acting on the south pole and then the force acting on the north pole would be equal. So the net force, so this is Fn and this is Fs, they're equal and opposite to each other because this is a uniform magnetic field. So the force acting on this and the force acting on that would be the same. So the net force is equal to Fn plus Fs, but then Fn is in the positive x direction and Fs is in the negative x direction, so this will be equal to 0. So the net force on this solenoid will be 0. But what about the torque? The torque is not 0 because it will start rotating, right? It will start rotating. So the torque is given by this expression mb sine theta. What should m? It's 1.28 ampere meter square. What should b? The b is 7.5 into 10 power minus 2 Tesla. So it is 7.5 into 10 power minus 2 Tesla, and the angle sine 30 is 1 by 2. So that should give you 0.64 into 7.5 10 power minus 2. So I can write this as 6.4 into 7.5 into, I multiplied that by 10, so divided by 10 will be 10 power minus 3, 10 power minus 2 into 10 power minus 1. So notice here, it is 6 times 7.5 would be, twice 7.5 would be 15. So 6 times that would be 45. Then plus 0.4, roughly half of it. So somewhere around 4 times that would be 0.3. So you're going to get 48. Okay, when you multiply these two, you get 48 into 10 power minus 3. So 48 into 10 power minus 3, or into like 4.8 into 10 power minus 2 Newton meter. So that is the torque experienced by this solenoid. So the net force experienced by the solenoid will be 0 because it is kept in a uniform magnetic field. So the force on the south pole will be equal to the force on the north pole. So the net force on the solenoid will be 0. But then because they are not acting in the same line, these two forces, they are acting in two different lines. So it will have an effect of torque on the coil. So you can find the torque, and that value is 4.8 into 10 power minus 2 Newton meters, but the net force on it will be 0. So that's the answer to that question. In 5.9, a circular coil of 16 turns and radius 10 centimeters carrying a current of 0.75 ampere rests with its plane normal to an external field of magnitude 5 into 10 power minus 2 Tesla. The same, like you have a circular coil and it's going to act like it has a number of turns, and it has an area, and it has current flowing through it, which means that you can have a magnetic moment for it. You can have an M for it. And it is in an external magnetic field of 5 into 10 power minus 2 Tesla. So you get that too. Okay. Then the coil is free to turn about an axis in its plane perpendicular to the field direction. So the axis of rotation is perpendicular to the field direction. So it can move in that field. The field direction is like that. Then like this coil is like this. So it can move about an axis which is perpendicular to the field direction. So that is what is said. When the coil is turned slightly and released, it oscillates about its stable equilibrium with a frequency of 2 Hertz. Then what is the moment of inertia of the coil about its axis of rotation? So they want you to find the moment of inertia now. So what are the things given here? This 5.9. The number of turns is given. So N is given to be 16. And then I is given to be 0.75 amperes. So radius is given to be 10 centimeters. So 10 centimeters is equal to 0.1 meter equal to 10 power minus 1 meter. Okay. So from that, can I find area of this? Can be pi r square. Pi r square. Pi is going to be equal to 3.14. Then r is 10 power minus 1 square. So I will have 10 power minus 2 meter square. So that's the area form. So I got NIA, and from this I should be able to find the magnetic moment of the coil. So M is equal to NAI or NIA. So that's going to be 16 into I is 0.75 into 3.14 into 10 power minus 2. So this 0.75 I can write as 3 by 4. So I can write it as 3 by 4 like that. So then this will cancel 4. 4 into 3, 12. 12 into 3.14. So we get 12 into 3.14 10 power minus 2. So what I'm going to get now? So this is going to give me 12 into 3.14. If I do that, it will be 314. See, 314 and then 628, 8, 6, 7, 3. So 37.68 into 10 power minus 2. So that's the moment, magnetic dipole moment of this coil. So M can be given to be 3.77 into 10 power minus 1 ampere meter square. So this M is given. What else is there? B is given. The external magnetic field B is given to be 5 into 10 power minus 2 Tesla. So 5 into 10 power minus 2 Tesla. Okay. So this coil is turning. So it's like this. So you have a field, magnetic field B, and then you have M. So this coil, this M. So now it is like when you slightly disturb it, then it is going to oscillate. So then the period of oscillation is also given. Okay. The frequency is given actually. So the frequency F is given 2 Hertz. That's the frequency. So then what I'm going to get now. Okay. So the frequency is 2 Hertz, which means the time is equal to 0.5 seconds. The period of oscillation. So you've got all this information now. So what are they asking you to find? They're asking you to find the moment of inertia of this coil. So we know that. What do we know? We know that torque, and do it here. Okay. Torque is equal to I alpha, and in this case it's a restoring torque, so you get I alpha is equal to minus mb sine theta, because it's small angle approximation, then you have theta there, so alpha is equal to minus mb by I into theta, and this is in the form of simple harmonic motion, which means that this will be omega squared, right? So in this case omega squared is equal to mb by I. So this I is actually the moment of inertia. So we have a different symbol, something like a stylish I. So they want you to find this I. So how do you find? Like I can bring all of these things here. So this is omega squared will be equal to 2 pi f the whole square. So that would be 4 pi squared f squared. Okay, then I can find I. So from this equation I can find. So this is something that we already done in the class. Okay, so I'm redoing it. That's all. So I from that expression is given by mb by 2 pi f the whole square. So I'm taking it here, omega squared comes down, so that's going to be 4 pi squared and then f squared. So that is going to be, my m is 3.77, is 3.8 into 10 power minus 1, and then my b is 5 to 10 power minus 2, and this would be 4 pi squared, right? So this is 4, pi squared is approximately 10, and f squared is 4 again. Okay, f squared is 4. So this is what I get. I can take this 10 up there as 10 power minus 1, so I'll get 10 power minus 4 as this. So 3.8 into 5 divided by 16 is what I will get. That's somewhere around 20 by 8. You can see that, right? Or let me multiply this anyway. 3.8 into 5 will be 19, right? So 90 into 10 power minus 4. So it says I mode of inertia is equal to 19 into 10 power minus 4, because I am bringing this 10 up there, that divided by 16. So this is equal to roughly 1 point, and this 3, so roughly 2. 1.2 into 10 power minus 4 kilogram meter square. So that's the answer to this question. So this is how we find the moment of inertia of the coil. That comes from here. This you already done in the class elaborately. I have just summarized it here, and when you do it, then this is the answer you get. Okay, let's move on to do problem 5.10. The magnetic needle, free to rotate in a vertical plane parallel to the magnetic meridian, has its north tip pointing down at 22 degrees with the horizontal. The horizontal component of the Earth's magnetic field at the place is known to be 0.35 Gauss. Determine the magnitude of the Earth's magnetic field at the place. It's a very simple problem. So 510. So what it says is that the tip, the north tip of the ball magnet or the magnetic needle, which is free to rotate vertically, at a place is pointing down at 22 degrees. And at that place, the horizontal component of the Earth's magnet has been measured to be some value. Then the question is, what is the Earth magnetic field strength? Not just the horizontal component alone, but the total field strength. So it's like this. If this is the horizontal plane, then the magnetic needle, the north, is dipping like this, and this angle is given to be 22 degrees. Okay? And at that place, BE or BH, I'll say the horizontal component of the Earth magnetic field, is given to be 0.35 Gauss. 0.35 Gauss. So they want you to find BE. But what is BH? BH is, okay, which means that like your B is in this direction, right? Okay. Because the needle is pointing down, which means the B is in this direction. And the horizontal component BH is in this direction. This is what you have measured. And what is a BH? BH is actually BE cos theta. Okay? So BH is equal to BE cos theta. So this is 0.35 is equal to BE. Theta is 22 degrees, so cos is 22 degrees. So cos 22 would be slightly less than 1. So your BE is equal to 0.35 by cos 22 degree Gauss. So this is going to be less than 1, slightly less than 1. So approximately this will give you a value of 0.38 Gauss. Very simple problem. So they have given you the horizontal component, and then they tell you the tip angle, which means that BE is in this direction. So they want you to find B. So BH is cos of that BE. And BE can be found easily this way. Very easy problem. Then 511. So 511 is this. At a certain location in Africa, a compass points 12 degrees west of the geographic north. The north tip of the magnetic needle of a dip circle placed in the plane of magnetic meridian points 60 degrees above the horizontal. The horizontal component of the Earth's field is measured to be 0.16 Gauss there. Specify the direction and magnitude of the Earth's magnetic field at the location. Okay? So what they're saying is that suppose this is a place in Africa, and let's suppose this direction is the geographic north. And when I keep a magnetic needle, then that needle is 12 degrees away from the geographic north, which means that the magnetic north is 12 degrees from the geographic north at that place. So it's going to, the needle is going to point like this. And not just that, the needle is also pointing up at an angle of 60 degrees. It's like this, which means your BE is in this direction. It's not going down, it is in this direction. So you must, from this you should understand that this space is south of the equator. It is not in the northern hemisphere, it's in the southern hemisphere. I want you to understand that. Okay. So from this they want you to find the BE. So let me draw this now. So let me take this picture. This is the Earth. Okay. And this is the geographic north. And here is the magnetic north. Okay. Which is actually the magnetic south pole. Anyway. So let's say this is the equator. Okay. And at some point in Africa, so this is Africa, something like that, okay. So at some point here, then you see that the angle, this is like when you keep a needle, it's going to point like this. So this angle, that is given to be 12 degrees. And not just that, it is also pointing up. It should point up, because why? See, if you look at the magnetic field lines, because they'll go from here to there, right? So it will be, so if you see it, it will be pointing up here, and as you go down, it will, as you go northwards, then it will point down. At the equator, it will be horizontal. In the south, it will be pointing up, and on the northern hemisphere, it will be pointing down, and at the north pole, it will point exactly down, vertically down. So this is what it is. From this, what you can do, the horizontal component of the field at that point in Africa is given to be 0.16 Gauss. 16 Gauss. And what do you know? You know that BE is actually equal to BH by cos theta. This is the dip angle. Right? This is dip angle. So now its dip is up anyway. So you get 0.16 by, at what angle is it dipping? The dip angle is 60 degrees up actually. Okay, I said it's up. The northern hemisphere, the north pole will dip, or the needle will dip. The southern hemisphere, north pole will go up. So that angle with the horizontal is 60 degrees. It's up. So cos 60. Cos 60 is 1 by 2, so that will come up there. So we will get 0.32 Gauss. So 0.32 Gauss is the strength of the Earth's magnetic field at that location in Africa, which is in the southern hemisphere. So you know that in Africa all the three lines will cross, the equator and the other two will cross. So like you can be on the other side. Okay. So like this is here, the value is given 0.32 and it will be up. Since point is there, and 60 degrees up. So that is how you figure this thing out. Hope this is clear to you. Think about it a little more. Then I will do 5.12. A short bar magnet has a magnetic moment of 0.48 joules per Tesla. Give the direction and magnitude of the magnetic field produced by the magnet at a distance of 10 cm from the center of the magnet on the axis, the equatorial lines of the magnet. So that's easy. So 512. We know this, like if you have a bar magnet, a short bar magnet, this is north and this is south, okay, this is center, then B at this axial line, okay, B, the axial line, is given by this formula, mu naught by 4 pi into m by r, or 2m by r cube along the axial line. And at a point on the equatorial line, or on the equatorial plane, then this is given by B is equal to mu naught by 4 pi into m by r cube. And that's all there is to it. Just put in the numbers and you get the answer. So this is going to be equal to, what is mu naught? Mu naught is 4 pi into 10 power minus 7 divided by 4 pi. This 4 pi and 4 will cancel, and then 2 into, what is m? The magnetic moment is given to be 0.48. 0.48. That divided by, the distance is 10 centimeters, right? This is 10 centimeters. This distance is 10 centimeter is equal to 0.1 meter. This is 10 power minus 1 meter. So this r cube, 10 power minus 1, the whole cube, so it will be 10 power minus 3. So this is going to be equal to, the whole thing will cancel with this, it will be minus 4, 10 power minus 4. 2 into 0.48 will give you 0.96 into 10 power minus 4 Tesla, or 0.96 Gauss along this point. And along this point, same thing, except that you're not going to get 2 there. So that is so, it's again 4 pi into 10 power minus 7 for mu naught divided by 4 pi, m is equal to 0.48 divided by 10 power minus 1, the whole cube. So this will cancel and this will get minus 4. So you are going to get 0.48 into 10 power minus 4 Tesla, or 0.48 Gauss. So this is a straightforward application of the formulas. Okay, we'll do problem 513. A short bar magnet placed in a horizontal plane has its axis aligned along the magnetic north-south direction. Null points are found on the axis of the magnet at 14 cm from the center of the magnet. The Earth's magnetic field at that place is 0.36 Gauss and the angle of dip is 0. What is the total magnetic field on the normal bisector of the magnet at the same distance as the null point from the center of the magnet? At null points, field due to a magnet is equal and opposite to the horizontal component of the Earth's magnetic field. Okay. This is a very easy problem to do, I mean, if you understand it. 513. there is this earth magnetic field. I mean, let me ignore the magnet first. The earth magnetic field will be in this direction. This is my north and this is my south. I told you that earth magnetic field line will start from the south and end with the north. So here the earth magnetic field line is like this. And if we were to keep a magnet, a bar magnet here, if this is the north, if we just suspend it, the north will align with this north and this is south. So the field line of the bar magnet will be in this direction. So notice here, along the axial line, the field of the bar magnet is the same, in the same direction as the direction of the earth magnetic field. So I can't just freely suspend it. I have to hold it and turn it like this. So my magnetic north must point to the south. Then the field line from my bar magnet would be in this direction. And the field line from the earth magnet will be in this direction. If at some point, if the magnetic field strength of this bar magnet matches with the earth magnetic field strength at that point, then both the fields will cancel, then you will have a null point. If you keep a magnetic needle there, it won't deflect at all. So that is what they mean by this. Okay, let's see. So let me take the north-south direction. Okay, first this is my north and this is my south. So the earth magnetic field will be in this direction. The earth magnetic field will be in this direction. So my magnetic field must be in the opposite direction, which means that if I keep a bar magnet not aligning with north, but I need to hold north like this and then south like this. In that case, the magnetic field due to my magnet will be in this direction. So at some point, which is given to be 14 centimeters from the center, at this point, which is 14 centimeters, along the axial line, then this is the value of my field is equal to the value of the earth field. So then it cancels. So I get the null point here. Okay, I want you to understand this. Okay. So notice here, this is north, this is south. Earth magnetic fields are in this direction, but I am not freely hanging this magnet. I am holding it in the opposite direction, which means that at some point, if the field strength of this is balanced by the field strength of the earth magnetic field, then you will have a null point here along the axis. And for this particular magnet, that is found to be 14 centimeters. Now the question is, at the same distance along the equatorial plane, the same 14 centimeters here, what would be the strength of the magnetic field, the combined magnetic field? Okay. First, we know one thing. Now what is that? At the same distance along the axial line, the magnetic field will be twice the magnetic field at the same distance along the equatorial line. So which means that if we find the earth magnetic field, the field strength to be equal to the earth magnetic field here, then the field strength has to be half of it in the equatorial plane at the same distance. Let me write here. Okay, so let's suppose this is the bar magnet, and then let's suppose that I find some B value at some distance x. And at the same distance, x in this direction, equatorial direction, now B will be B by 2 of this. So we know that from the equation. So that this is the idea that we are going to use. Okay. So you know that at 14 centimeters, the vectorial plane, this will be opposite to, this will be half of the earth magnetic field, because at 14 centimeters it is equal to the earth magnetic field. So here this is going to be half of that. And which direction would it be? Notice here, if this is my north, then the field line will be like this. So the field line here at the 14 centimeter will be in the same direction as the field line of the earth. I told you the field line of the earth is from south to north. Now I am holding this magnet in the opposite direction. I am not freely hanging it. If I freely hang it, then it will go here, then it will align, the equatorial line will align with the earth magnetic field, so I will get no null point. But if I hold it in the opposite direction, this will send out field like this, and earth is sending field like this. So at some point the fields can cancel, it can become 0. And if I hold the magnet like that, then notice the field line will be like this from north to south. So at this point, the equatorial plane, the direction is like that. But the earth field is also like that. So they will add at 14 centimeters. Okay? So let me hold this. The earth, let me draw this like that. Earth field lines are like this. Okay? And the magnet, I am holding it like this. My north is this way now, south. So notice here, it's going to be like this. So this should oppose the field, right? So that is when you can get a null point. Okay. Now you notice here, and the equatorial plane, this is in the same direction as that one. So what would be the net field at that point? The field due to the earth magnet, and also the field due to your Bohr magnet. So this point will have the sum of both. So the field strength will be stronger here. So we said in this problem this is 0.36 Gauss. Earth field is 0.36 Gauss. Okay. So now at 14 centimeters, okay, at 14 centimeters here, this will be 0.36. So at a distance of 14 centimeters, this is 0.36 Gauss. This, but it is in opposition, so you get a null point here. But here you will have half of it. For the same distance, you will get half of it, so 0.18 Gauss. But that is in this direction. So 0.18 plus 0.36, the net field is equal to field due to the earth magnet plus field due to the Bohr magnet. So that is equal to, this is 0.36 plus 0.18. So that's going to be 0.54. Okay. So this is how you do this problem. I want you to understand this problem. The next problem, 514, now builds on this idea. If the Bohr magnet in exercise 513 is turned around by 180 degree, where will the new null points be located? Okay. So now it was in opposition. If we turn this in the other side 180 degrees, now 514. Okay. Same B. B is in this direction. The earth magnetic field is in this direction. But now I am going to turn this magnet around. So I am going to have north here and then south here, 180 degree turn. So then you notice here, okay. So this is how the field lines are going to be. You notice here, along the axial line, there is no way you can get a null point. Because notice this field is in the same direction as the field of the earth magnet. So you will never get cancelled. But here this can cancel. Notice along the equatorial plane, along the vertical line, notice the line is coming like that now on the opposite direction, so it can cancel here. So I can find a point along this. So what would that be? Well, how do I do this? I know that to get a null point here, the field strength must be equal to the earth magnetic field. Yes? So I should get BE at this point. Then what distance would it be from here? That's the question. Let's see. At 14 centimeters, I'll get some value. Yeah? From that I can find the magnetic dipole moment. Let's see. I can find the magnetic dipole moment of this field. M, okay, first let's see. B is equal to mu naught by 4 pi to M by R cube. Okay. Let's say you said like at 14 centimeters along the axial line, then you got that to be equal to the earth magnetic field, but in that case axial line equation would be mu naught by 4 pi into 2m by r cube, and this was equal to the earth magnetic field, which is 0.36 Gauss. So you knew this value, that is 14 centimeter cube. So I can say that my m in this case is going to be equal to m in this case is going to be 4 pi into 10 to the power minus 7. So 4 pi and 4 pi will cancel. Then I can find my m this way. This is 14 centimeters. So this was equal to 0.36 into r was 14 into 10 to the power minus 2 the whole cube. Okay, and now I've got 10 to the power minus 7. So as it goes here, this will become 10 to the power minus plus 7, and this divided by 2. And once I find m, then what should I do? All I have to do is, at this distance, at some distance here, it must be equal to the earth magnetic field. I hope you understand this. So what I have done here, using this example, I found m. I know that at 14 centimeters, the magnetic field strength of this magnet was equal to the earth magnetic field along the axial line. So using that information, I find the m of the bar magnet. And once I find m of the bar magnet, then along the equatorial plane, what is this axial? So along the equatorial, this must be equal to mu naught by 4 pi into m by r cube. If I need to find a null point here, then this must be equal to 0.36 here. So at what distance would it be 0.36? I got m. I got all these values. So can I do it? So it's going to be 4 pi to 10 to the power minus 7 by 4 pi. M I got here 0.36 into 14 into 10 to the power minus 2 the whole cube into 10 to the power 7. So divided by this, I don't know what r cube is going to get. Okay, this 4 pi and 4 pi will cancel, and what will I get? 10 to the power minus 7 and 10 to the power 7 will cancel. So I get this, but this must be equal to 0.36, right? So at that distance, that is when you will get a null point here. So 0.36 and 0.36 will cancel. So I can get r cube is equal to, I need to get 2 here. 2 is missing. R cube is equal to 14 into 10 power minus 2 the whole cube by 2. So if I take the square root, the cube root of this, then R will be equal to 14 into 10 power minus 2 into, okay, here this will be 2 to the power 1 by 3. I need to take the cube root of 2 and multiply it. So this will give me 14 into 10 power minus 2 to 2 to the power minus 1 by 3. So if you get this value, and if I do that, this would be about 11.1 into 10 power minus 2 meters or 11.1 centimeters. So at a distance of 11.1 centimeters, the field strength along the equatorial plane is equal to 0.36. So at those points, they will, because you kept the magnet like this, will cancel. You won't have a net magnet field, you get null points there. So that's how you know this problem. Lastly, problem 5.15. A short board magnet of magnetic moment, not movement, it's wrong, spelling mistake there. A short board magnet of magnetic moment 5.25 into 10 power minus 2 joule per Tesla is placed with its axis perpendicular to the Earth's field direction. At what distance from the center of the magnet the resultant field is inclined at 45 degrees with the Earth's field on its normal bisector and B, its axis. So the magnitude of the Earth's magnetic field at the place is given to be 0.42 Gauss. Ignore the length of the magnet in comparison to the distances involved. Okay. So what does the problem say? It says there is a board magnet with a magnetic moment of 5.25 10 power minus 2 is placed with its axis perpendicular to the Earth's magnetic field direction. Okay, so let me say this is 5.15. 5.15. So let's say this is the Earth's magnetic field. It's in this direction. Now what is happening is you are keeping a board magnet with its axis perpendicular to the Earth magnet. This is north, this is south of this. This is DE. And here you will have this. Like that. So this is your axial line and this is your equatorial line. Now they ask you to find that okay, they give you one more information. What is that? They say that it is 45 degrees. The resultant field is 45 degrees at some point here along the axial line and at some point here along the equatorial line. So what is the resultant field? The resultant field is the sum of these two. So let's say let me take this point here. This is point 1. If the resultant field is to be at 45 degrees to the Earth magnetic field, then you should understand that the field strength here due to this magnet must be the same as the field strength of the Earth magnetic field. Why? Because only when you have equal vectors, you will have the resultant at 45 degrees. So if this is the Earth magnetic field and at that point your B due to this board magnet must be equal to B. Only then the resultant of these two would be at an angle 45 degrees to B. So how do you do this then? How do you find the distance from there? It's very easy. At this point, at some distance r, this must be equal to b along the axis. So what is b, the bar magnet at some distance along the axis? This is mu naught by 4 pi into 2m by r cube. Okay? So which means that I can put in numbers here. No? So this is 0.42 is what is given. 0.42 is the earth magnetic field into 10 power minus 4 Tesla. So this will be mu naught by 4 pi. I will take it as 10 power minus 7, because 4 pi 10 power minus 7 divided by 4 pi will give you 10 power minus 7, and then you get 2 into, what is my m here? My m would be, my m is given as 5.25 into 10 power minus 2. So 5.25 into 10 power minus 2. So that divided by r cube. Okay. So now this will be 10 power minus 3 and minus 5. So now I can find r cube is equal to 2 into 5.25 into 10 power minus 5 divided by 0.42. Okay. And from here I can find r. So if I take the cube root of this value, I will get r. So at that distance, point P1 along the axial line, if I take the net field, the vector sum of both the fields, that would be at 45 degrees to the earth magnetic field. So this is how I do this part. And coming back to this point, same other equatorial, same thing. So notice here too, at this point, if the resultant has to be 45 degrees, then B value here also must be equal to B to give me 45 degrees net field. But what is that here? BB here must be this one. And I'll call this as P1, and then this is 0.2, let's say BB2. It's equal to mu naught by 4 pi. Now I don't have 2m because it is on the equatorial plane, so I get m by r cube. So if this also must be equal to 0.42. Only then I get, this is 0.42, the earth magnetic field is 0.42 here, and this must be 0.42. Only then I will get a resultant of 45 degrees. Okay? So that is going to be equal to the same thing, except that you won't have a 2 in this equation. So I will get my, if I plug in all these numbers, my r cube in this case is going to be equal to, without 2 I will get this 5.25 into 10 power minus 5 by 0.42. So if I take the cube root of this, then I will get that value at the distance, where the resultant field will be at an angle of 45 degrees to the earth magnetic field. So this is how I do this problem. Hope this is clear to you.